Welcome to another interesting class today. We want to be looking at applications of differential calculus, which we can also call differentiation. So we are looking at application of differentiation. And the first thing we are going to be looking at is going to be rate of change. We'll be looking at rate of change. This is one of the major applications we'll be looking at today with respect to what we have learned in the concept of differentiation, function of a function, logarithmic function, chain rule. Everything we have learned will be seeing an application on rate of change. And the next one we'll also look at today is rectilinear motion. We want to see how the concept of rectilinear motion applies, how the concept of differentiation applies to rectilinear motion. So rectilinear motion is a major thing we are going to be looking at today. Now let's begin as we look at what rate of change is. The y dx can sometimes be interpreted as the rate at which y is changing with respect to x, which we have an example on the screen. The a dt, that's the rate of change of a, which is the a dr times the r dt. We'll be getting this understanding in this example we'll be looking at. Let's quickly look at this example. We have a question before us right now that says the side of a cube is increasing at the rate of 5 centimeters per second. Find the rate of increase of the volume when the length of a side is 3 centimeters. This question is what we are going to be looking at. The side of a cube is increasing at the rate of 5 centimeters per second. Find the rate of increase of the volume when the length of a side is 3 centimeters. So let's quickly make a sketch. We have a cube on the board. Of course, we know what a cube looks like. A cube has all its sides equal as against a cuboid. A cube has all its sides equal. So this let's assume the length of the sides are labeled x centimeter, x centimeters, x centimeters, as we see on the screen, just to depict the cube we are talking about. The side of a cube is increasing at that rate 5 centimeters per second. It means every 1 second, this length of the side increases by 5 centimeters. And the volume for cube is V equals to x raised to power 3. That's the volume of the cube, and that's how to begin. So we'll be looking at the rate at which volume changes with respect to x, which we can write as dv dx. Now let's analyze the question. Let's look at the analysis we have concerning the question. We have dv over dt. That's what we are looking for. Find the rate of increase of volume, which is dv dt. When we say rate of increase of the volume, that's dv dt. When our x that we are given in this question is equal to 3 centimeters, the x given is 3 centimeters. Don't forget your rate of change, rate of increase of volume is dv over dt, and our x given is equal to 3. Our x given is equal to 3. Now we are given that rate 5 centimeter per second. So imagine the size of this particular thing, this particular cube, in 5 seconds. Okay, that means the size will have grown bigger, like 5 times in 5 seconds if it increases 5 centimeter for every second. That's the interpretation of the x dt. And according to the question, it means our dx dt will be equal to 5. That is the rate of increase of the cube in what? In 1 second, which is 5. So let's look at it again. The v dt is what we are looking for. We're given the value of x to be equal to 3, and our dx dt is equal to 5. Why? Because the rate of change given in the question is 5. Now, how do we find dv dt? This is what we call connected rate of change. For us to have dv dt, which is the question we are requested to find, let's write our dv all over. Then we are supposed to have something at the denominator, but let's watch. And the other one, let's put our dt at the denominator that way. Okay, so we have dv dt. So what do we put at the denominator where we left vacant, and at the numerator where we left vacant? We're expected to put our dr in such a way that the r still cancels the r. So what we are simply applying here is the concept of chain rule, or what we call function of a function we have before. Then you can easily see what we have is now dv over dx times dx over dt. We have dv over dx times dx over dt. Okay, so this dv dx times dx dt depict what we learn in what? Chain rule. Remember, we did chain rule, which we also called function of a function. What's our chain rule again? dy dx equals to dy du times du dx. So if we differentiate dv dx, we have 3x squared. V is equal to x raised to power 3. So that's what you have on the screen right now. Our dv dx is what? 3x squared. Remember how to differentiate. 3 comes behind and you remove 1 from the power. Okay, that's that. So our dx dt from the question is 5. So we need to substitute 5 there. So what becomes our answer? It will be 15x squared. 15x squared. But remember, our x is equal to what? Our x is equal to 3, because we are given in this question that x is equal to 3. X is 3. So we are going to be substituting x in our dv dt now. We have obtained our answer partially as 15x raised to power 2. So the next step now is to substitute 3 so that we can actually get dv dt. That's our specific answer. So we're going to be putting our 3 in 15x squared. And if I put that, it will be 15 times 3 squared. It's going to give us 15 times 3 squared, which is 15 times 9. So our answer is expected to be 135 centimeter squared per centimeter cube per seconds, because we are dealing with volume and not squared. So it's going to be centimeter cube per second. That will be our unit, because we are dealing with dv dt. So okay, so our answer is showing on the screen right now, which is 15 times 3 squared, which is 135. Good. Let's quickly consider the second application of differentiation we are looking at today, rectilinear motion. What does rectilinear motion mean? This is the motion of a particle along a straight line. This is the motion of a particle along a straight line. So the velocity v is written as the x dt, where x is the what? The displacement. Good. If the particle is momentarily at rest, at that point when the particle is momentarily at rest, our velocity is equal to 0. And I just showed you now that velocity is the x dt. The x dt is equal to 0. So our acceleration is what? In terms of v, dv dt. So acceleration can also be known as the 2x over dt squared. So minimum and maximum values is also another concept of application of differentiation. But for this particular one, we'll be looking at it extensively in our next class. And I just want to give you an insight into it, that minimum and maximum values is what we'll be doing in our next class. So these are the conditions necessary for a minimum point at x is equal to a, meaning at a particular point. So at both minimum point and maximum point, the first condition necessary is our dy dx is equal to 0, and the 2y over dx squared is greater than 0 for minimum. Okay, so